This time we talk now about a different nucleophilic addition reaction, and that's the reaction or addition of Grignard reagents on aldehydes and ketones. Grignard reagents are nucleophilic, which means they can attack carbon of the carbonyl group in aldehydes and ketones, and not only aldehydes and ketones, also in other carboxylic acid derivatives. Okay, so that's because Grignards are nucleophilic. Carbon in the carbonyl group is electrophilic. If we do this general representation for the reaction, for example, that's an aldehyde. If you react it with a Grignard reagent, and if you remember, Grignard reagents have the general representation of RMGX, where X is a halogen. So two steps in this nucleophilic addition reaction. The addition first of the Grignard, so R prime, for example, just to make it different from that RMGX, with, in the subsequent step, reaction with the hydronium ion or protonation, and the product that's obtained is this, and this is actually a secondary alcohol. This is an aldehyde. So an aldehyde reacts with the Grignard reagent, so it's RMGX, that is the Grignard, to give a secondary alcohol. This group R prime comes from the Grignard. We will see this in nucleophilic addition very shortly, mechanistically. So this alcohol product is a secondary alcohol with more carbons, and that more carbons or extra carbons in R prime again comes from the Grignard. But why do Grignards attack? Why do they behave as nucleophiles in this nucleophilic addition reaction? What do we know about Grignards, or how do we form them? Well, Grignards are formed if you take, for example, a primary, well, in general, a primary alkyl halide or an alkyl halide or an aryl halide. You react this with Mg, magnesium metal. So you take an alkyl halide or aryl halide with, and you react it with magnesium. So what happens is that a Grignard is formed, and if you look at the structure of alkyl halides, you will notice that that there is a shift of electrons or withdrawal of electrons by the halogen, which makes that carbon adjacent to X or bonded to X in alkyl halides electrophilic. So this carbon is electrophilic now. If you look at this CMGX, well, the scenario is actually different. In this case, that's because magnesium is a metal. It's a metal or an element in group 2A. It's an alkaline earth metal. Carbon is obviously a non-metal, so the non-metal, being more electronegative, will pull electrons toward itself than the metal. Metals are positive, so the shift of electrons is now actually the opposite. Carbon would pull electrons toward itself in this CMG bond, so it leaves a positive delta on magnesium and a negative delta on carbon. If carbon here, because of this shift of electrons, because of the higher electronegativity of X relative to that of carbon here is electrophilic. If you look at that carbon, and because of this different shift of electrons, that's because carbon is more electronegative than magnesium, carbon now will behave as a nucleophile. So carbon in this case is actually nucleophilic. And this is a remarkable shift in reactivity, if you like. Alkyl halides are electrophilic, and if you do this reaction with magnesium, now that carbon in the Grignard becomes nucleophilic. Not only is actually nucleophilic, but it is also basic. So Grignards are nucleophilic at carbon that's bonded to magnesium. Not only that, they are also basic. So Grignards are nucleophilic and basic. Now, because of that, this reaction must be carried out under an inert atmosphere. with exclusion of moisture, because if there is moisture here in addition with the Grignard will simply be destroyed and the corresponding alkane will be formed. And another important requirement for this Grignard formation reaction is that this magnesium has to be in the elemental form. It has to be in the free state. In other words, the oxidation state of magnesium must be 0. And if you notice the oxidation state of magnesium in the Grignard, it's actually +2. Magnesium has inserted itself in this CX bond. If you like, magnesium has added itself between the CX bond. Okay, now its oxidation state has increased from 0 to +2. Therefore, this is oxidation in chemistry. So this is oxidation, plus it is also insertion. So magnesium has inserted itself between carbon and X, or has added itself between carbon and X. Therefore, this reaction is called oxidative addition or insertion. Oxidative addition or insertion, it's called oxidative. That's because the oxidation state of magnesium has increased from 0 to +2, and it is called addition or insertion because magnesium added or got added between carbon and X. So it is really crucial for magnesium to be in the elemental form. Otherwise, this oxidation step or oxidative addition step or oxidative insertion step will simply not work, because if you use, for example, magnesium chloride, where magnesium has +2 oxidation state, this oxidative addition step or oxidative insertion step will never take place. So it is really important for magnesium to be in the elemental form for the Grignard formation reaction to take place.